Hi everyone, so here we're going to talk about how electrons are actually located in these different orbitals or sublevels. So we're talking about the rules for filling them. So one of the first rules is the off-ball principle. Off-ball said that electrons will go to the first energy level, fill that first, and then go up to the next energy level. Paul exclusion principle said that only 2 electrons can occupy a particular orbital, and that they must have an opposite spin. So one's clockwise, the other one's moving counterclockwise. And Hund's rule says that electrons are going to be evenly distributed in the orbitals before they get placed back into other ones. So let's take a look at this image. We have on the left-hand side energy increasing, and on the x-axis we actually just show you kind of like the different placements. So the S's go first, then the P's, the D's, and the F's. So here we have 1s, and then 2s. The next energy level will be 2p, then 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. Okay, so this again shows you just the energy levels and which one's the lowest energy, which one's the highest energy. So let's take for example potassium. We know that its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. And we just use the reference table or the periodic table to help us out with that. So the first one, we're going to take the 1s2. So right here is the 1s is located here. So one electron is going to be shown by an arrow, an up arrow, and the other one is going to be shown by a down arrow. So this is showing that the electrons actually have opposite spins. So again, each one of these lines represents an electron. So the next one will be 2s2. So I have one going up, the other one going down. Then we have 2p6. Now if you look over at the p's, there's 3 different versions of p. There's px, py, and pz. So first, since we have to put 6 electrons in here, we actually put them evenly in each one of those 3 spots. So 1, 2, 3, and then go back for Hund's rule to fill them back in. So 1, 2, 3, 4, 5, 6. Then we go to 3s2, so 1, 2, opposite directions, and then 3p6. So again, 1 orbital, 2, 3, then go back to the first orbital 4, 5, and 6, and then 4s just goes up. So there's one lone electron in that 4s area. So this is what your orbital filling diagram would look like. We would leave the others blank because there aren't any electrons in those. All right, so then, so that's potassium. Let's go ahead and take a look at calcium. So calcium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So just like with potassium, we'll go ahead and fill them in. So 1s2, we have one going up, the other going down. Again, these lines are representing the electrons. And then 2s2, so 1 electron going up, 1 electron going down to show one's going clockwise, the other's going counterclockwise. Then we have 2p6, so we go 1, 2, 3, and then 4, 5, and 6. 3s2 is 1, 2, 3p, oops, that was supposed to be 3p6, 1, 2, 3, 4, 5, 6, and then 4s2, 1, 2. So calcium is actually pretty stable because all of its orbitals are full. Now if we're going to show an ion, we would show that, in fact, it would end up losing the electrons from this 2s sublevel and just show this as the calcium ion. If we were going to show the electron excited state, we would show that actually one of these electrons might move up to another sublevel. So this 3p might actually go up to the 3d instead. Again, that just shows the excited state. The 4s could also move up to there as well. So this again is how you fill in the electrons for these orbital diagrams. To summarize, make sure that when you put these electrons in, there's only 2 electrons in an orbital, one goes up, the other goes down, and that you fill in the levels first and then go, put 1 electron in each sublevel and then fill them in as you go back. We'll be practicing a few times. See you later.